All right, so number 17 in in our chapter 2 test review. It gives us that f of x equals 3 plus 20 over x squared minus 4, where x does not equal positive or negative 2. Because we know that if we put positive or negative 2 down here in the denominator would be 0. Alright, so we have a graph here that looks somewhat like this. Alright, this is positive, negative 2. This is point A. Alright. And it asks us to find the coordinates of A. Now we see here that at A, it is the only maximum, local maximum of the entire graph. So this means that at A, the tangent of the line that goes through point A, that's tangent to the curve, the slope equals 0. And that is the only point within the entire graph where the tangent of the line equals 0. So this means that our derivative of this would have to equal 0. Now let's find the derivative. So f prime x, we know that that's the derivative of 3 plus the derivative of this. And we know that the derivative of 3 equals 0. So we know that f prime x equals the derivative of just 20 over x squared minus 4. Alright, now we know that this looks like a fraction, so we need to do the quotient rule. We first find that the derivative of 20 equals just 0. And the derivative of x squared minus 4 equals 2x. Yeah, it's just 2x. Alright, we could find that by using the derivative formula. So f prime x equals f of x plus h minus f of x over h. So here we have, if we are trying to find the derivative of this, that's f of x for now. We do, now let's call this g of h. Alright, so we have we expand x plus h squared, which is x squared plus 2xh, minus negative x squared minus negative 4, which is positive 4, all over h. Let me see, these cancel out. That equals 2xh plus h squared over h. Because as h goes to 0, it doesn't matter if h ever reaches 0 or not, so we could cancel the h's out without having h never equals 0, because h is never going to go into 0. So that equals a limit as h goes to 0 of 2xh over h, which is 2x, plus h squared over h, plus which is h. And as h goes to 0, as this gets infinitely smaller, it just becomes irrelevant. So our limit of our derivative of of x squared minus 4 equals just 2x. Alright, so we just proved that. We just proved what we found easily by using the derivative rule. Okay. So we now know the derivative of 20, and we know the derivative of x squared minus 4. And so to find the derivative of 20 over x squared minus 4, it's just the derivative of 20 times x squared minus 4 minus the minus 20 times the derivative of x squared minus 4 over x squared minus 4 squared. And that is our quotient rule, which states that the derivative of f of x over g of x equals f prime x times g of x minus g prime x of f of x over g of x squared. Alright, so that's what we did right here. This is still our derivative of our original function up here, right? So we know that the derivative of 20 equals 0, so that's just 0 times x squared minus 4 minus 20, and the derivative of x squared minus 4 is 2x over x squared minus 4 squared, that's x to the 4th power minus 8x squared plus 16. Alright, so 0 times x squared minus 4 equals 0, so that's just negative 40x over x to the 4th power minus 8x squared plus 16. Alright, so this is our derivative, which helps us find the slope of any tangent line that crosses through a point on the curve. So we know the slope's 0, so this must equal 0, which means that negative 40x equals this times 0, which is 0. And so x equals 0 over 40, which is 0. So, which is really obvious. A is on this point, and it crosses the y-axis, so x equals 0. So our coordinates are of A is at 0 and some y value. And if we plug 0 back in as our x in our original function, we get that the y value f of x, 3 plus 20 over 0 squared minus 4. And that equals 3 plus 20 over negative 4, which equals 3 plus negative 5, which is equal to negative 2. So we finally get that our coordinates at A equals 0, negative 2. Alright, that's part A. We're going to keep the derivative over here so we know that next time, that the derivative of this equation equals negative 40x over x to the 4th power minus 8x squared plus 16. All right. Okay. Now, we're still in part A. There are two parts to part A. We need to show that when f prime x, the coordinate, the derivative of f of x, when that equals 0, it's at point A. Well, we just found that A equals 0, negative 2. So we need to find that when this equals 0, x equals 0 as well. Alright, I'm not sure how we do that. Okay, so let's first set the derivative equals 0. So negative 40x over x fourth minus x squared plus 16 equals 0. That's what we're setting equal to, right? So negative 40x equals 0. And so x equals 0. And when x equals 0, that's a coordinate right there. Alright, I guess that's how I proved it. Alright, so that was the second part of part A. Now we're at part B. So it says that our second derivative, so this is f prime x, right? So f double prime x, I forgot what it's called, is the derivative of our derivative of f of x. So the derivative of our derivative is 43x squared plus 4 over x squared minus 4 cubed. Alright. Okay, so using this second derivative, so part 1 of B is to justify that the graph has a local maximum at A. Alright. So this shows us, our derivative of our derivative shows us whether the slope of the derivative of our original curve, which is the slope, has any change. So like if there's an acceleration or not. So we want to find out what happens to the derivative of the derivative at point A, which is when x equals 0. So when x equals 0, that equals 40 times 3, 0 squared plus 4 over 0 squared minus 4 cubed. And that equals 40 times 4 over negative 4 cubed. And that equals 40 times 4 over 4, and that's all negative 4 cubed. Because 4 times 4 times 4, when it's negative, is going to be negative. So we can cancel out. That's 4 cubed, right? We'll cancel that out. This equals 10. So that equals negative 10 over 4, which equals negative 5 over 2. And because the derivative of the derivative at point A is negative, that means our slope of the curve, our slope of the tangents slightly decreases. I don't know what I'm saying. So we know that there must be a maximum. There must be a local maximum. All right. Now, part 2 of B, explain why the graph of f does not have a point of inflection. So at points of inflection, let's say for like this curve, for an example, the slope here continues to decrease, right? But at the point of inflection, the slope neither decreases nor increases. Because, like, take the graph of time, speed, time, velocity, and acceleration, for example, in physics. Acceleration is the derivative of the derivative. Speed is the velocity is the derivative of time and distance. And and acceleration is the derivative of velocity. And so when at the point of inflection, the speed neither increases nor decreases. So the acceleration there is at 0. So at a point of inflection, f prime of x, I don't know what it's called, f double prime of x equals 0. And that means 0 equals our equation 43x squared plus 4 over x squared minus 4 cubed. So that means 0 equals 43x squared plus 4, which means 3x squared plus 4 equals 0. Wait. Which means, I don't know, 40 equals 0, if we divide that. And 40 cannot equal 0. So this point doesn't exist, which means there's no point of inflection. And that's why the graph doesn't have a point of inflection. Alright. Now we're at what part are we at? Part E. No, part C. Describe the behavior of the graph of f for large absolute value of x. And that's just the IB stupid way of saying the absolute value of x as it goes to infinity. Alright. So, I mean, when we look at the graph, we can tell that as it goes to infinity, it reaches some sort of asymptote. But, well, we'll just have to prove that with math. Okay. So, with math, we prove that the asymptote, the horizontal asymptote of f of x is the asymptote of 20 over x squared minus 4, which is when y equals 0. But you add 3 to that, so it's y equals 0 plus 3. So our asymptote's when y equals 3. So y can never equal 3. And we could obviously tell as x goes to negative infinity, y goes to 3. As x goes to positive infinity, y goes to 3. Why is that? Do I have to prove that mathematically? No, I'm not gonna do it. Okay. So the answer to part C is as the graph of x goes to large of positive infinite of large absolute value of x, which just equals 3. All right. Write down the range of f. The range of f is from negative infinity to positive infinity, but there's some asymptotes in there. So we know here that x, well, the range is just all the values of x, right? And x cannot equal positive or negative 2. So the range of x is from negative infinity to negative 2. Union, it's solve parentheses because it cannot equal 2. Negative 2 to positive 2. And then union positive 2 to infinity. That's our range. And that's it. We're done with number 17.